This is the fourth and last lecture of chapter 17, which looks at substitution reactions involving aromatic compounds. Keyword aromatic. So in this presentation, we'll do a quick review of electrophilic aromatic substitution reactions involving benzene. Of course, as I mentioned earlier, benzene is used a lot as our starting material because it is readily available, and of course it's one of the best examples of an aromatic molecule. Next, we look at the electrophilic aromatic substitution, this time involving heteroatoms. So there will be other atoms and not including carbon and hydrogens. In particular, we look at those that have nitrogen, pyrrole, and pyridine. Lastly, we'll look at a different type reaction. This time it involves a nucleophilic aromatic substitution. So look out for that change. We'll shift from electrophilic aromatic substitution to nucleophilic aromatic substitution of aromatic molecules. Okay, so let's begin. As a review, you will recall that the general substitution reactions for aromatic compounds, and using benzene as our classic example, is shown here. So we have a hydrogen, and if that's replaced with an E plus, an electrophile, to get a substituted benzene with an E here, and of course the proton comes off, this is our substituted benzene as our product. So here are the reactions that we have covered so far. Nitration of benzene. Don't forget, this is the real reagent here that generates the electrophile, and the electrophile is NO2 plus, and here is the catalyst. Bromination of benzene. Bromine is the reagent, and of course Br plus is the electrophile, and here's the catalyst that makes that happen. Chlorination of benzene. Chlorine is the reagent, and Cl plus, of course, is our electrophile, and it all happens because of the catalyst iron trichloride. Alkylation of benzene is shown here, where we have an R alkyl group bonded to a leaving group such as chlorine in the presence of an Lewis acid as a catalyst. We have a substitution. These type reactions also known as the Phil-Crafts alkylation. Don't forget, the electrophile here is a carbocation. So it's possible for rearrangement to occur because of that R plus carbocation. Here is another type, the acylation of benzene, where the acyl group here is the carbonyl. And this is known as the Phil-Crafts acylation of benzene. And lastly, we looked at the sulfonation of benzene, where this here is the electrophile and this is the catalyst. Another aspect that we looked at was the substituted benzene, the reactions of substituted benzene with an electrophile E+. We pointed out that if there is a pair of electrons adjacent to the ring, it will donate electrons into the ring, making this electron rich. So therefore, the reaction with E+, I'll write it over here, would be very favorable. The electron density will be increased in the ortho and para direction, a position, but the major product here is the para because of crowding if it were to be placed in the ortho position. So that is why these substituents here are described as ortho para directors, because it activates the ring towards substitution in the ortho and para locations. Here's the other type substituent that we looked at, and this is the meta director or deactivating. We mentioned that if there is a double bond adjacent to the ring, it tends to pull electrons from the ring and onto the more electronegative atom here, oxygen. So it deactivates the ring because it's pulling electrons from the ring. And if this is a reaction that reacts with E+, as you can imagine, it's not as favorable. That's why it's called deactivating groups. What happens here is that it makes the ortho and para position more positive, leaving the meta position less positive. So if there's a reaction, the reaction will occur to give this as the major product, the meta. That's why it's called a meta director, because it directs the electrophile from here into the meta position. It's called deactivating because it pulls electrons from the ring. This is called activating because it gives electrons to the ring, increases the electron density, and increases the electron density primarily in the ortho and para positions. So let us look at another molecule, in this case the molecule that's called pyrrole. And the difference here is that it has a nitrogen. It's still aromatic because here are 6 electrons in that ring. Key, however, is that the dipole moment is not 0 as was the case of benzenes. It's not 0. So the dipole is pointing towards the ring. So these electrons here are pointing towards this ring and not necessarily right around this nitrogen, even though it's an electronegative. But the electrons are circulating here. So as you can see, with that happening, this molecule here can undergo an electrophilic aromatic substitution, as shown here. So here's pyrrole, and here's E+. But as you can see, there are 2 positions here that are different. We call this number 1, number 2, and number 3. So the electrophile can substitute here or here. So 2 possible products. Of course, if it went on this side, it's the same as here, and this would be the same as here. So there are really 2 possible products. How do we determine which is the major product? Because of course, as you know, in organic chemistry, we carry out a reaction so we can get a target molecule in the highest percentage yield. How do we know that? Let's see. Look at the mechanism. So in the first step of the mechanism, or the rate determining step, because the aromaticity is destroyed by the addition of E+ to the pyrrole here. So what that gives is this carbocation here, or this intermediate, if the substituent goes here, or the electrophile. If the electrophile goes here, it gives this intermediate. The bottom line is, out of these 2 intermediates, this one and this one, which is more stable? Why do we need to know that? Because the more stable intermediate will lead to the major product. This intermediate here on top is more stable because we can draw more resonance structure for this intermediate compared to this intermediate here. So therefore, this intermediate on top is more stable than this, and this intermediate here will lead to the major product, in which there is a addition of the electrophile in position number 2. Let's look at the final step. In the final step, as you can imagine, the H comes off as a proton, leaves its electrons behind. These electrons swing in to form the aromatic compound. These other electrons are still here, so that's aromatic. So as you can imagine, this is a fast step to generate the aromatic compound. This would be the major product. Why major product? Because that is the product that is coming from the most stable intermediate. Same aspect here, a loss of proton to give proton here. These electrons swing back in to give that double bond. These electrons are still here, so this is aromatic, but this is the minor product. Why minor? Because that is coming from the intermediate that's not as stable as the intermediate that's generated from this reaction. So here's a reaction in which we have pyrrole here reacting with this set of reagent that you are familiar with. Here's the nitric acid, which will generate NO2 plus in the presence of the catalyst H2SO4. So it can add either here or position number 3. And of course, as we know from the previous slides, the intermediate that gives the most stable, the addition that gives the most stable intermediate will lead to give the most stable product or the major product, and this is it. And of course, this is the minor product. So if you're asked to predict the major product for this reaction, this would be the major product. Let's look at another reaction. This one involves pyridine. It has a nitrogen, a heteroatom, nitrogen, so it's a heteroatomic aromatic compound. In this case, however, experimentally, it's determined that the dipole moment points away from the ring and towards the nitrogen. So in other words, the electron density in here is not equally distributed as the case for benzene. It's more distributed towards nitrogen. So as you can imagine, this is not very reactive. So let's see if we can get it to react with an electrophile based on these 6 electrons that are still in the aromatic system. Just to illustrate that the dipole moment is really pointed towards nitrogen, here's some resonance structures. So if we draw a resonance structure for benzene, here's one, and you can see that the negative charge is here and the positive. We can delocalize the positive charge toward the ring, but the bottom line is that the negative charge is right here and here, which means that that's the most nucleophilic end of the molecule. So these electrons that are in the ring are not very reactive, but we can still get them to react under the right set of conditions. So let's see what should happen. If we get them to react, there are 3 positions here. We call this 1, 2, 3, and 4. So it can go either here, because we're looking at substitution for the hydrogen. Substitution here, substitution here. So we get 3 possible products. Notice we will not get a substitution on this because there's not a hydrogen for that substitution to be carried out. So there are 3 possible products here. How do we know which is the major product? You know the system to determine the major product, and that is to look at the mechanism. So we have to look at the mechanism to determine which is the major product. We'll have to look at the mechanism to determine which is the most stable intermediate, because we know the most stable intermediate will lead to the most stable product. So let's look at this. So first, let's add the electrophile here. As you can see, we're using these electrons here to swing out and add to the electrophile, putting it here, and there's a positive charge right here. We can draw resonance structures as shown here. However, there's one resonance structure that's not stable. Why? Because there's a positive charge on the very electronegative nitrogen, and there are 2 bonds to nitrogen. You know, typically nitrogen has 3 bonds or 4 bonds if it has a positive charge. So this is not stable. So the resonance structure that are shown here for the stability of this intermediate, there's one that's not stable. So the overall resonance structure for this intermediate is not very stable. Let's look at putting it in this position, the 3 position, which means we're taking these electrons here and swinging it out to make a bond to E plus, and here are those electrons. So therefore this is a positive. We can draw resonance structures as shown here, and notice that all of these resonance structures here, they look pretty good. We're not putting a positive charge on a very electronegative atom. They're all on carbons as shown here, which is not bad. So this intermediate here is at least more stable than the previous one, where the electrophile was placed here. Let's look at the third possibility, putting the electrophile here. As you can imagine, again, these electrons swing out to bond to our electrophile here to make this bond right here, and the positive charge is here. We can draw resonance structures here, and you can see we're back to this again, where that's not stable resonance structure. So that means that we're putting a positive charge on a very electronegative nitrogen, and this nitrogen has a pair of electrons, and it also has 2 bonds to it. So it's not very stable. At least it's not as stable as putting it on the previous, as shown in the previous slide, where it's here. So conclusion is that if you have pyridine and it reacts with an electrophile, you get all 3 products, but one is the major product, and this is it on the carbon number 3. Why? Because if it's placed on carbon number 3, the intermediate that leads to that product is more stable than the intermediate that leads to these other 2 minor products. So this is the major product. Let's look at a specific example here. So here's pyridine. You recognize this brew because here's the electrophile NO2 plus, and here's the catalyst, and the substitution will go here. I should point out, however, this is under heat, and of course we know why, because pyridine is not reactive, because these electrons are not readily available because they're more towards the nitrogen. So it's very reluctantly coming out and bonding to the electrophile here. So we have to give it a little bit of energy, heat for that. And notice it's the major product and in low yield. Why low yield? Because it's not very reactive. I should point out here, however, that this is just one example of the electrophiles that we have used. All of the electrophiles that we've used before, the Cl plus, the Br plus, etc., they can be used here because all we need is an E plus and an appropriate catalyst to get the reaction to go. And for this reaction, since these molecules are not reactive, we may have to apply heat and or pressure. Okay, let us look at another type reaction. This type reaction is called nucleophilic aromatic substitution. Notice it's not electrophilic aromatic substitution, but nucleophilic. You may be saying to yourself, this should not work because the benzene ring here has electrons. The nucleophile has electrons by definition. The nucleophile is a nucleus-loving, or Lewis base has at least one unchaired pair of electrons. So why would electrons react with electrons? We have learned before that should not occur because unlike and like repel each other. But one thing that may happen here is that we have a good leaving group, such as the chlorine. If there's a good leaving group, we have extreme conditions such as high pressure and high temperature, we can force this to come in here and kick that out. So the product would be, if there's a reaction, and there is, if there's a reaction, we're substituting this leaving group here for the nucleophile as shown here. Notice that if we're hydrogen, the reaction would not go, because hydrogen is a very poor leaving group. As a matter of fact, extremely poor. So that would not work. You need a good leaving group here, which will leave as a stable conjugate base. So L here is the leaving group, and Nu is the nucleophile. Let's see what's required for this reaction to work. One thing that we can do to make this reaction go is to add electron withdrawing groups. Electron withdrawing groups to the benzene ring. Just based on the description here given by the name, electron withdrawing groups are pulling electrons from the ring onto the groups here. So as you can imagine, if you're pulling electrons from the ring here, it makes the ring more electrophilic, which means that a nucleophile such as this can come in and kick that out to give this as the product. Typically, we have to apply heat or pressure, and I'll get more into that in a second. So this would be the substitution product, because we have a good leaving group here, and we have a nucleophile here. We have electron withdrawing groups pulling electrons away from the ring, so the reaction can occur. Let us look at the effect of having the nitro group here, though, which is shown here. So in the mechanism, you'd expect this pair of electrons to attack this carbon. Why this carbon, not any other carbon? Because it's bonded to the leaving group, because here is a polar covalent bond making this partially positive and that partially negative. So it attacks right here. As you can imagine here, there is, here's a negative charge, so we can do resonance here. And of course, in the final step, this leaves as the Cl minus to regenerate our aromatic ring right in here, which of course, as you know, is stable. So that's another driving force. So this would be the fast step. And of course, this would be the slow step, rate determining step. And the fast step to regenerate the aromaticity here. But notice we said electron withdrawing group. What is it really doing? Let's look at the next slide here. So if we have this, for example, here's the nucleophile bonded to this carbon, and these electrons are now delocalized in the ring. But it's possible for these electrons to be delocalized onto the oxygen. So here are these electrons here, and here they are. So we're moving electrons into the oxygen from the ring, making this electrophilic so that the nitrogen nucleophilic group can attack the ring. You may be wondering, are there other electron withdrawing groups? And yes, they are. Those are the same electron withdrawing groups that we looked at when we looked at deactivating groups for the electrophilic aromatic substitution. I don't want to confuse you, but when we looked at deactivating the aromatic ring of benzene, we looked at pulling electrons from the ring, so that makes it less reactive. Here we're pulling electrons from the ring so it can be more reactive towards a nucleophile. So in other words, if a benzene ring were bonded right here, and we had a similar situation here, we had a nucleophile, for example, and a chlorine, and of course we had the here, and the electrons are right here. and of course a negative charge. Let's put a negative charge here. These electrons can swing here and onto the nitrogen. So as you can see, it's pulling electrons onto the nitrogen from the ring. Same here. So if you had a aromatic ring here, and you had your group back here, such as a nucleophile and a chlorine and a pair of electrons right here with a negative charge, these electrons can come in and onto the oxygen. So you can see it's pulling electrons onto the oxygen. That's why it's called electron withdrawing groups. So that's why it works. Let's look at some examples here. So here is chlorobenzene. Chlorine, good leaving group. Sodium hydroxide, good nucleophile here. Very extremely good nucleophile, Lewis base. There are no electron withdrawing groups here, but extreme heat and pressure causes this to come in and that to leave, to give the substituted product, and that's known as phenol, of course, and of course the side product is the chloride. Same thing here. We can use here the amide, anion, and that reacts with the chlorobenzene here. Here's your leaving group, and this is aniline. So this gives a method to make aniline from chlorobenzene. Okay, let's turn our attention now to a very unusual observation. Very unusual observation. If we label this carbon here with an isotopic carbon, I know, carbon 14 for example. Of course, you know, carbon that's in natural abundance is carbon 12. So let's use a labeling for this carbon right here. If we should do the nucleophilic substitution, here's the nucleophile, it's coming in here and going here, we'd expect this to be the only product where the substitution occurs here and this leaves. But there's another product here where this labeling is adjacent to it, which would imply that the nucleophile also came in here. So as chemists and as scientists, we need to explain that, because this is experimental. Folks went in the lab and actually did this experiment and noticed that there was a scrambling in which we have 50% of this and 50% of this labeling, where the labeling are in different locations. How do we explain that? There's a very unusual explanation, and creative explanation, might I add, and still used for that to explain this strange reaction. So what is the first step in this mechanism is that the strong base, which is also nucleophilic, abstracts the hydrogen adjacent to the leaving group, creating a triple bond. As you can imagine, that's highly unusual, because you know, a triple bond here, the bond angle would be 180 degrees because it's linear, but here the bond angle is not 180. So it has a unique name. We call that the benzyne intermediate. Very unstable, but it's used to explain the observation, the experimental observation. So in the next step, the nucleophile can attack here, and in the presence of the solvent we get this product. There's an equal probability of it attacking this carbon to give this, and in the presence of the solvent we get that. Notice it's an equal probability of attacking either carbon. So that would explain an equal scrambling, an equal mixture, 50-50 mixture here for that type substitution reaction. So again, as chemists, we go in the lab, we carry out experiments, we have different observations, and as scientists, we have to explain these observations so that when we do the experiment again, we know what to expect. So that's why I'm encouraging you students to be creative in your thinking, not just to memorize the material, but to be creative in your thinking, in coming up with solutions. All right, let's look at a couple more reactions involving pyridine. So here is pyridine, and I drew this again just to show you that the dipole moment points in the direction of the nitrogen. So here's a positive, here's a positive carbon, here's a positive or less electron distribution at these points. And see, so if we have a nucleophilic aromatic substitution, it would work best if the leaving group were placed in this position or this position. Why? Because it's the most positive. And a nucleophile which has a pair of electrons will prefer to react with a positive or a partial positive. So this reaction is favorable, even though we have to heat it, but it's favorable in this position to give a substitution. Notice the substitution here is bromine is being substituted here for the nucleophile to give this product and this as the inorganic product. Another example here before we conclude. So here is again a substituted pyridine, good leaving group. Notice a very good leaving group, bromine. Here is our nucleophile. As you will recall, this is an organometallic. Lithium is to the left of the periodic table. Carbon is to the right. So this is a polar bond where this is partially negative, in fact almost ionic. So this is negative here and this is positive here. So here is our nucleophile, that entire group, and this carbon here is the nucleophilic carbon. So this carbon will react here and this will leave, so this is our product. Same here. This is our nucleophile, all of that. This is our nucleophilic carbon, which will react right here, and this bromine will leave to give us this as the product and this as the inorganic product. I think this is the end of chapter 17. So once again, as you have seen, chapter 17 is very involved. Lots of different concepts. So you take your time reading it through, working lots of problems, making sure you understand the concepts, and equally making sure you can apply these concepts to solving problems. As I've been saying all semester, we're not just here to memorize organic chemistry and to learn facts, but we're here just as well to apply that thinking to solving problems so we can become better scientists. Okay? Continue to study.